Brand new Toyota engines failing before 40,000 miles with scored main bearings. GM V8 trucks needing complete valve train replacements at 60,000 miles from collapsed lifters. Honda turbocharged engines experiencing catastrophic low-speed pre-ignition that punches holes through pistons. We used to measure engine life in decades and hundreds of thousands of miles. Now we're measuring it in lease cycles, 3 years, 36,000 miles, just long enough to get past the factory warranty before catastrophic failures start appearing. Today, I'm performing an autopsy on the modern engine and exposing exactly why legendary manufacturers like Toyota, GM, and Honda are suddenly facing engine failure rates that would have been unthinkable 20 years ago. This isn't bad luck. This isn't isolated defects. This is a perfect storm of government fuel economy mandates, aggressive cost-cutting, and engineering decisions that prioritize emissions compliance over durability. Let's tear this apart. Toyota built a reputation on bulletproof reliability. The old 2JZ inline-6, the 1UZ V8, the 22R-E 4-cylinder. These engines ran for 300,000 to 500,000 miles with basic maintenance. You could neglect a Toyota engine and it would keep running. That reputation sold millions of vehicles. But something has changed fundamentally in the past 5 to 7 years with Toyota's newest engine platforms, and it's causing failures that owners never expected from the Toyota name. The problem centers on Toyota's Dynamic Force engine family, the new generation of 4-cylinder and V6 engines introduced starting around 2018. These engines use extremely high compression ratios, 13 to 14 to 1, compared to 9 to 10 to 1 in older designs, to maximize thermal efficiency and meet fuel economy standards. Higher compression extracts more energy from each drop of fuel, but it also creates higher cylinder pressures and temperatures that stress components more severely. To achieve these compression ratios while maintaining power output, Toyota designed these engines with thin-walled cylinder construction, lightweight pistons, and tighter bearing clearances than ever before. The manufacturing tolerances are incredibly tight, measured in thousandths of a millimeter. This allows Toyota to meet efficiency targets, but it creates almost zero margin for error in manufacturing or assembly. And that's where the failures are occurring. Toyota has issued multiple technical service bulletins and recalls for dynamic force engines with machining debris left in crankcase passages during manufacturing. These tiny metal particles, fragments from machining operations that weren't properly cleaned out, circulate with the oil and get trapped in bearing surfaces. The debris scores the bearing material, creates hotspots, and causes rapid wear that leads to bearing failure at 30,000 to 50,000 miles. I've diagnosed Toyota Camrys and RAV4s with a 2.5-liter dynamic force engine that developed severe engine knock and low oil pressure before 40,000 miles. Teardown revealed scored main bearings and crankshaft journals damaged by debris contamination. These are catastrophic failures requiring complete engine replacement, and they're happening in vehicles that are barely out of the warranty period. The root cause is manufacturing quality control, failing to keep pace with engineering tolerances. When you design an engine with clearances so tight that a few particles of metal debris can cause bearing failure, your manufacturing process has to be absolutely perfect. Every engine block has to be perfectly cleaned after machining. Every assembly step has to be flawless. But Toyota is building millions of engines per year across multiple global plants, and maintaining that level of perfection at scale has proven difficult. The pressure to manufacture quickly and cheaply while meeting aggressive efficiency targets has created a situation where even legendary Toyota quality control isn't catching all the defects. And when a defect makes it through debris in the oil galleries, improperly torqued bearing caps, contaminated assembly lube, the engine has no tolerance to compensate. It fails rapidly and catastrophically. Now let's talk about General Motors, because their V8 engine failures are even more widespread and even more predictable. GM's modern V8 engines, the 5.3-liter and 6.2-liter used in Silverado, Sierra, Tahoe, Suburban, and Escalade, are experiencing valve train failures at alarming rates. The culprit is active fuel management and its newer version, dynamic fuel management. These systems deactivate cylinders under light load to improve fuel economy. When you're cruising on the highway, the engine shuts off half or all of the cylinders, and you're essentially running a V4 instead of a V8. In theory, this saves fuel by reducing pumping losses and friction from deactivated cylinders. In practice, it creates uneven mechanical stress that destroys lifters and camshafts. Here's what happens mechanically. When a cylinder deactivates, the lifter for that cylinder's valves collapses and stops following the cam lobe. But the camshaft is still spinning, and the cam lobe is still there. The transition between active and deactivated states puts side-loading stress on the lifter that it wasn't designed to handle continuously. Additionally, the deactivated lifters aren't getting the same oil flow and pressure as active lifters. Oil delivery to valve train components is designed around the assumption that all cylinders are firing and all lifters are moving. When half the lifters are collapsed and stationary, the oil flow pattern changes. Some lifters get inadequate lubrication. Over tens of thousands of activation and deactivation cycles, wear accumulates. The lifter roller bearings start to pit and spall. The cam lobes develop wear patterns. Eventually, a lifter collapses completely or a roller bearing seizes, and you get the dreaded lifter tick, a distinct tapping noise from the valve train that indicates imminent failure. If you keep driving, the failed lifter damages the camshaft, and metal debris circulates through the engine-damaging bearings and other components. I've diagnosed GM trucks with lifter failures at 50,000 to 80,000 miles, well within what should be the prime of the engine's life. The repair requires removing the cylinder heads, replacing all 16 lifters, replacing the camshaft if it's damaged, and cleaning out all the metal debris. The cost is $4,000 to $7,000 if you're out of warranty. And the failure rate is high enough that GM has extended warranties on some model years and issued multiple technical service bulletins, but they haven't fundamentally fixed the design flaw. The root cause is that GM prioritized a few percentage points of fuel economy improvement to meet CAFE standards over long-term durability. Active fuel management saves maybe 5 to 7% fuel in highway cruising, barely noticeable to the driver, but it subjects valve train components to wear patterns they weren't engineered to handle. And when the lifters fail, it's not covered under warranty past 60,000 miles, so the owner pays thousands for a repair caused by a design flaw. Now let's zoom out and look at 3 fundamental technologies that are killing modern engines across all manufacturers. These aren't isolated to Toyota or GM. These are industry-wide trends driven by emissions and fuel economy regulations that sacrifice durability for compliance. First technology: gasoline direct injection. GDY sprays fuel directly into the combustion chamber under high pressure rather than into the intake port, like traditional port fuel injection. This improves combustion efficiency and power output, but it creates a major problem: intake valve carbon buildup. In port injection systems, fuel washing over the intake valves keeps them clean. In GDY systems, the valves never see fuel. They only see crankcase vapors from the PCV system, which contain oil mist and combustion byproducts. Over time, these deposits bake onto the intake valves, forming hard carbon buildup that restricts airflow and changes valve seating. At 50,000 to 80,000 miles, GD1 engines develop rough idle, misfires, reduced power, and poor fuel economy from carbon-caked intake valves. The only fix is walnut shell blasting or manual cleaning, which costs $400 to $800. This is a maintenance requirement that didn't exist with port injection, and it's hitting owners who aren't prepared for it. Worse, severe carbon buildup contributes to low-speed pre-ignition, LSPI. This is a phenomenon where carbon deposits or oil droplets in the combustion chamber ignite prematurely under high load and low RPM conditions, creating a secondary flame front that causes extreme cylinder pressure spikes. LSPY can crack pistons, damage rings, and destroy bearings in a single event. It's catastrophic and instantaneous. Manufacturers have mitigated LSP1 with oil formulations and engine calibrations, but it remains a risk in turbocharged GDY engines, especially when combined with carbon buildup and extended oil change intervals. I've seen engines with holes blown through pistons from LSP1G events at under 60,000 miles. Second technology: auto start-stop. This system shuts off the engine when you stop at a traffic light and restarts it when you release the brake. It saves a trivial amount of fuel, maybe 2 to 5% in city driving, but it subjects the engine to conditions it wasn't designed for. Every time the engine stops, oil pressure drops to 0. When it restarts, there's a brief moment, half a second to 2 seconds, where the engine is cranking and running before oil pressure builds and reaches all bearing surfaces. That's a dry start. In a normal engine life, you might have 50,000 to 100,000 starts over 200,000 miles of driving. With auto start-stop, you can have 200,000 to 300,000 starts over the same mileage, triple or quadruple the start cycles. Each start causes a small amount of wear. Multiply that by 3 or 4 times as many starts, and you're accelerating bearing wear, ring wear, and cylinder wall wear significantly. The fuel economy benefit is minimal. You're saving maybe $50 to $100 per year in fuel. But the accelerated wear from constant start-stop cycles could easily cost you years of engine life. I've seen engines with 80,000 miles that have bearing wear patterns consistent with 200,000 miles in older vehicles. The only variable is auto start-stop cycling. Third technology: ultra-thin oils like 0W16 and 0W8. Manufacturers are pushing thinner and thinner oils to reduce friction and meet fuel economy targets. But these oils provide dangerously thin protective films between metal surfaces, especially under heat and load. When oil temperature hits 230 to 250 degrees, common in turbocharged engines or under towing loads, 0W16 thins to the point where film strength is marginal. Add any fuel dilution or viscosity shear, and the oil can't adequately protect bearings and cylinder walls. I've seen oil analysis from engines running 0W16 that shows viscosity dropping out of grade by 5,000 miles and wear metals spiking by 7,500 miles. The oil is literally too thin to do its job under real-world stress, but manufacturers spec it because it improves EPA fuel economy testing by fractions of a percent. Combine all three of these technologies: GDY carbon buildup contributing to LSPI, auto start-stop multiplying wear cycles, and ultra-thin oil providing minimal protection, and you get the perfect storm for early engine failure. So how do you protect yourself when you're driving a modern engine that's engineered to meet regulatory targets rather than last 300,000 miles? Here's what you need to do. First, ignore the 10,000-mile oil change interval completely. Change your oil every 5,000 miles maximum, regardless of what the manual says or what the maintenance reminder tells you. Modern engines with GD1, turbocharging, and thin oil specifications cannot safely run 10,000 miles between changes in real-world driving. Fuel dilution, carbon contamination, and viscosity shear degrade the oil too quickly. 5,000-mile intervals ensure you're always running on fresh oil with full protective capability. Second, use top-tier certified gasoline exclusively. Top-tier fuel has significantly higher detergent additive levels than non-top-tier brands. Those detergents help control GDY carbon deposits and keep injectors clean. It's not a complete solution. You'll still need intake valve cleaning eventually, but it delays buildup and reduces severity. If you're already experiencing rough idle or reduced power from carbon buildup, use a high-quality fuel system cleaner like Chevron Techron or BG44K every 5,000 miles. These cleaners won't remove baked-on intake valve deposits, but they'll control injector and combustion chamber deposits. Third, disable auto start-stop if possible. Some vehicles allow you to permanently disable this feature through programming or with aftermarket devices. If yours doesn't, make it a habit to manually disable it every time you start the car. Yes, it's annoying, but it's less annoying than replacing bearings at 100,000 miles from accelerated wear. Fourth, consider upgrading to slightly thicker oil if your engine allows it based on overseas specifications. If your engine runs OW16 in North America but OW20 or 5W30 in other markets, you can safely run the thicker oil for better protection. Check owner's manuals for your vehicle in international markets to see what's approved. Fifth, drive the engine hard occasionally. Modern engines with GD1A benefit from periodic high RPM, high-load operation that burns off carbon deposits and heats the engine thoroughly. Highway drives at sustained speeds, occasional wide-open throttle acceleration, and allowing the engine to reach full operating temperature help prevent deposit buildup. Sixth, if you're buying new, avoid first-year models with brand-new engine designs. Let other people beta test new platforms. Buy proven engines with a few years of production history so manufacturing issues have been identified and corrected. Here's the bottom line. Modern engines from Toyota, GM, Honda, and other manufacturers are failing earlier than previous generations because of aggressive efficiency engineering driven by government mandates, tight manufacturing tolerances with inadequate quality control, and technologies like GD1, auto start-stop, and ultra-thin oils that sacrifice durability for regulatory compliance. You can't change how these engines are designed and built, but you can absolutely change how they're maintained. Frequent oil changes, quality fuel, disabling start-stop, and proactive carbon control will extend engine life significantly beyond what the average owner experiences. Is your modern engine still running strong? Or have you already had a warranty claim for early failure? Drop your vehicle, engine type, mileage, and any issues you've experienced in the comments. Let's see which brands and engine platforms are actually holding up. And if this just exposed why modern engines fail earlier than the ones your parents drove, hit that like button. Next week, I'm showing you actual teardown photos of failed Toyota and GM engines with the exact damage patterns I described today. You need to see this. If you're not subscribed, hit that button now. Drop a comment. I respond to everyone. Thanks for watching. I'll see you in the next one.